Welcome to this short presentation on curvature. I'm very excited about the new formula for the product of graphs. So what I show is that the curvature for graphs is compatible with the Shannon multiplication of graphs. So let me do a classical board work. Here's the table of content. I start with reminding about curvature. So first of all, we have always a finite simple graph. All these results hold for any finite simple graph. It's a very nice category of objects. Of course, we always take the Whitney complex on it, and so this is very rich mathematical structure, and you can do topology, you can do any topology with this structure. If you believe into a little bit into non-standard analysis, this is it. This is the whole math. So what you have is a finite simple graph, and we have the curvature. So let me just make the notation. So S of x is the unit sphere. Unit sphere is the graph generated by all neighbors. So for this, in this case, if you take a vertex here, we take all neighbors, we take the graph generated by that, and that's a new finite simple graph. So that's the unit sphere, and we have, for any graph, we have f vector. So fk is the number of k dimensional simplices. Simplices are faces, are complete subgraphs, are cliques. There are lots of different names for that, and this forms a vector. So we have f0, the number of vertices, f1, it's the number of edges, etc. But it doesn't stop with one-dimensional simplicial complexes. That's the castration you can do on graphs, which is, I think, is a scandal that you have this restriction of graphs to something still interesting, but it's just infinitely many more interesting if you are looking at the right structure. And Whitney had this already this vision. Whitney was working on manifolds and graph theory here. So this is the f vector, and once you have that notion, you have a notion of Euler characteristic, for example. So for example, so we have the sum minus 1 to the k f k j. So this k is equal to 0. That's the Euler characteristic. If you look at interesting theorems in mathematics, most of them deal with Euler characteristic. That's one of the basic things. So it's the number of vertices minus the number of edges plus the number of triangles minus the number of tetrahedra, in this case 2, and So in this case there is no higher dimensional version. We don't count these faces here, that would be just silly because we have no idea what we actually call faces. So in this case the f vector is 11, 22, 10, 2. So in this example here we have we have 11 vertices, we have 22 edges, we have 10 triangles, and we have 2 tetrahedra, and the Euler characteristic is -3. So this is the Euler characteristic. Now there is a Gauss-Bonnet formula which emerged in the 19th century by Eberhard first, and then it was used in graph coloring. Mathematicians like Birkhoff or Hirsch have used this heavily, everybody working on graph coloring. And then it in the 80s, so it was a little bit generalized by Gromov, Higuchi, some Japanese mathematicians, and and then it around MIT, so there were a couple of mathematicians, Levitt and Foreman or Evako, they have kind of found a general relation. But I don't think it was really realized that this is the real deal. There is a real, this is the real curvature which belongs to the Gauss-Bonnet chain curvature which you have in higher dimensions. It's the real deal, what I'm telling you. So this is so what we have is the curvature is k of x. So what we have is 1, and then we take minus, and then we take f0 of s of x over 2 plus f1 s of x over 3 minus f2 s of x over 4 and so on. This is the curvature. So it's almost too trivial to be appreciated that this is really the right curvature. When I started with this in 2012, I just mentioned this in the introduction also. I was not really kind of appreciating this enough because I was working on manifolds. In manifolds, just in each dimension, got formulas for that. Essentially got the Dane-Somerville relations in that paper, 2012. And so I call this actually maybe the Levitt curvature, because I think Levitt was the first who really kind of formulated this. And so this is very easy to prove. What you do is you take the zero-dimensional parts and you leave that, and then you take the one-dimensional parts. You count so the zero-dimensional parts. That's kind of what you have at the vertex, and then the one-dimensional parts belong to zero-dimensional parts in the unit sphere. But because of this Euler handshake, what it is just this contribution -1 which you have in the Euler characteristic. This goes to both vertices. For a triangle, it goes into 3, so that's why you actually distribute it into 3. So this is also can be reformulated as a so let me just not write too much here. So if you define the f function, so f of g of t is 1 plus f0 t plus f1 t squared. So that's the sum k equal to -1 to infinity fk g. So that's that -1, you would just count it like that. So that's the f function, and what you can see is 1 minus f of g minus 1. That's the Euler characteristic. And this curvature is very natural if you write it with the f function. So k of x. So k of x, that's just the integral from -1 to 0 f g t dt. That actually you take here S6. So this is a very, 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 very natural, so you can just write it as an integral. So this is kind of my ultimate way how you can see this curvature. But what I realized over the last 10 years is that this is really, especially with integral geometric consideration, this is the same in the, in the continuum limit than all these fancy curvatures which you have in differential geometry. And you can derive this. So this is very nice. So let me just mention just a few names here. So there is a So Eberhard was actually doing much more. So most of the curvature considerations were in smaller dimensions, like polyhedra, considered for polyhedra. So for example, if you have a two-dimensional polyhedron and then the curvature, so when you have a so in this case it's 1 minus the degree, which is the degree. Over 6. So when you have d equal to two-dimensional manifolds, so when you look at that and you have only in the unit spheres. Unit spheres are one-dimensional spheres, and so you have the same number of vertices than edges. Then 1/2 minus 1/6 is 1/2 minus 1/3 minus 1/2 minus 1/3 is 1/6. And so you get this formula which has been used already or known already by Eberhard, who saw it already as a Gauss-Bonnet formula. He did much more than that. He showed which kind of configurations are really possible in a polyhedron, satisfying constraint to the Gauss-Bonnet formula, that the sum of the curvatures is equal to 2. That's what you have for a two-dimensional sphere. So that's pretty early, and then it came kind of used. If you look at mathematicians like Birkhoff or Hirsch, graph coloring. Essentially, everybody working in graph coloring was using this curvature at some point, because you want to, for example, show that there is a point where the vertex degree is smaller than 6. So 5, for example, or 4, and so that's in the context of, and then etc. Gromov was actually so I think 1998 was extending this a little bit, not in higher dimensions, but just extending this formula a little bit, using vertex degrees of the neighbors. So that was kind of something which is, and then in the 1990s, so that's where this kind of like Levitt, Foreman, Ivako, it's kind of hard a little bit to point down. And I got to this in 2012. So especially in manifold situations, and I've since used this all the time for various things. Of course, this paper, like 99% of what I would submit, is never even getting a reverie report, so that didn't get a reverie report even. But somehow it was good, because what happened is I could pretty quickly afterwards, I could get much more results, like the Lefschetz formula, or the integral theoretical things, which for example shows that for an odd-dimensional manifold, discrete manifold, curvatures are 0, which is not even an issue in topology. You don't even consider curvature of an odd-dimensional manifold, because the Gauss-Bonnet formula is a Pfaffian. Actually, by the way, just all the code which I have for what I'm talking about here is here, and just all the code together is maybe it's a fraction of what you need just to define in the neither the same programming language to do the Gauss-Bonnet churn implementation. And I've done that also for manifolds. I can compute that for any manifold and compute with Gauss-Bonnet churn, but it's just even for small dimensional manifolds which have some you know, which are not just, you know, rotationally symmetric. It's already quite a hike to compute this Riemann curvature tensor, so R, I, J, K, L, and then sum up over all these things. So this is quite a hike. And then you have to do that at every point. And here what we have is a discrete structure, and so this Gauss-Bonnet, I should just mention, so Gauss-Bonnet, kind of the highlight here. Actually, it's Gauss-Bonnet churn. It's as general. It's actually much more general. We don't give, you know, we don't care at all whether it's a manifold structure or not. It can be arbitrary, which is pretty cool. So, so what we are doing today, we are looking at the curvature of products. So if you're looking at graphs and you look at what is a kind of a good notion of a product, you're first tempted to look at products which preserve manifolds. And there are such products. I was actually looking for that also, just computer assisted. Essentially found the Stanley product, which is essentially just gives you that. It gives you from two manifolds, it gives you again a nice manifold, a nice manifold structure. But actually you don't care something. It's not associative notation if you don't stay in the ring. But if you, this is kind of like a barycentric refinement. If you multiply with 1, you get the barycentric refinement. So it is a, but it satisfies all the properties which you have, and actually it's very much related. Actually, kind of from a homotopy point of view, it's the same than the Shannon product. And that's the second thing which we are going to look at. So that's I call this just multiplication. So I talked about this kind of a couple of weeks ago. What we have is we have a very nice ring. So this category of graphs has an algebraic structure. It has a discrete. It has an addition, which is the disjoint union, and then we have a multiplication, which is the Shannon multiplication. This produces a very nice commutative associative ring. So let me just write that down here. So I call this Z. And then we have a plus, and then we have I call this star. It's the multiplication, and then we have a 0 element, which is the empty graph, and then we have a 1 element, which is K1. This is the Shannon ring. Commutative associative ring containing Z plus, which is the ring of integers. And I talked about this, right? If you take graphs which don't have any edges, if you look at Pebble mathematics, that's our mathematics. All the mathematics we do is Pebble mathematics. This is a mathematics which extends this to numbers which are more interesting, and then you can complete this also to a, Banach algebra. essentially it's just an infinite dimensional linear algebra, but it's very nice so that we can actually talk about real numbers, kind of the analog of real numbers here. So already the number theory is very interesting. I talked about this a little bit. So most graphs are prime. For example, they're also additive primes. The additive primes, this is an additive prime because it's connected, but it's also a multiplicative prime. You can check that very easily because there are 11 vertices, if there's a prime number of vertices. But if you just count the number, if you look at the sieving, the usual sieving argument which the Greeks have done, you see already that, you know, almost all graphs are prime. So it's quite an interesting thing. I joked it's the mathematics of the 22nd century, but it's not a joke. This is actually the mathematics which you can do. It's a very, very, very nice structure, and you can do lots of so essentially do whatever you want to do in this usual ring of integers, which extends into the, you know, the real numbers, complex numbers, etc. You build all these structures up. You can do that also here. But it's a little bit more costly because the multiplication is this Shannon multiplication introduced by Shannon in the 50s, and in an alternative, just dual way by Sabidussi. So there are various multiplications which we have for graphs, but this is the deal. This is the real multiplication which you want to do. Because, for example, so this has a very nice property. So, not only number theoretical or geometric or so, but for example algebraic topology. So for example, if BKG is the Betti number, actually the Betti number you can, I always brag about this, you can compute this in 6 lines of Mathematica without any code, any additional libraries or anything. So just by computing the kernel of the blocks of the Hodge Laplacian. So by Hodge theory. It's very, very nice, and you get explicit representative of the cohomology classes. And you can multiply them, actually here, this is just a tensor product produces with a cup product in cohomology. So the whole thing is very, 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 very natural. And also here, if you look at the Poincare polynomial, k is equal to 0 to infinity, so this is, we call this t to the k. So this is EGT. This is the Poincare. Then this is there's a ring homomorphism. So G to PGT is the ring homomorphism from this ring Z to the ring of polynomials. So this is pretty cool, and so that's essentially Kunet. And I mentioned Kunet is just very straightforward because you can immediately get what happens with the cohomology class. You can just multiply the cohomology classes. You have tensor products. So you take these harmonic forms, you multiply them, you apply the divergence, and you get a new cohomology classes of the product. So this is very, very explicit. Of course, what we have to do is first, this ring here contains already also negative graphs, like negative numbers. You introduce negative graphs. It's a growth of the completion of the monoid of, this joint union addition. And then, of course, you have also to extend here the Betti numbers. For example, so you say bk of minus g is minus bkg. Well, this is very natural. You extend the cohomology just to the whole ring, and so you have a nice cohomology ring. It's also it's actually kind of also ring homomorphism to the cohomology ring, if you like that. So I just mentioned this because shows this is really the real deal. This is the Cartesian product. Even so, what happens if you take two manifolds, two discrete manifolds, and you multiply them, you don't get a discrete manifold already. So, for example, you take a cyclic graph and you multiply it with a cyclic graph. Cyclic graph is a one-dimensional. So then what you get is so what happens is, so you have here, maybe I'll make 4. So this is C4. So C4. And what you do is, so you have here your C4. This point is identified with this. So this is a discrete torus. And this is also identified with this. So these points here, these are identified. This is really discrete torus, but what we have is, that's actually kind of a product which is very bad product. This is the small product. There's also the tensor product, which is just doing this. But if you combine this product, kind of what we sometimes is called the Cartesian product, with this, then you get the strong product, which is the Shannon product. So this is also a strong product. So what you do is, if you have two vertices in this Cartesian product of vertices, so you take the Cartesian product of vertices of this graph with this graph, and then you connect to, if the projection onto both graphs is either a point or an edge. So that's what you do. So this is actually the graph which you have in a chessboard. The king connection. If you look at that, so the neighbor's unit sphere. If you kind of look at that, that's the unit sphere. So it's the kind of a product one looks at in statistical mechanics. So this is, but it is a very nice product. It's associative. It's essentially the only product you really need in graph theory, and it has been done by Shannon already. Shannon mentioned a possibility to do arithmetic here, and he was, of course, as a young student already, he was doing arithmetic, the Boolean algebra arithmetic for circuits and things like that. So he was very aware that power of arithmetic, but he decided not to go into the arithmetic of these networks. So this has this is but it's a very interesting story. So that's the Shannon ring. So I mentioned that the product of two manifolds is not a manifold, but it's actually homotopic to a manifold. So this is, if you're looking at that, it's kind of just like a donut, which is kind of, there are some overbookings of things. It's kind of stronger. It's bound together stronger than just in a manifold where you have a triangulation. But who gives a damn? Well, what happens is you have the cohomology works. You have from a homotopic point of view, you have all the properties which you have for manifolds. If you look at this space here, so there's all the evidence points out that this space I'm living in here, we are living in here, is three-dimensional. Not time, but just it's three-dimensional, and you can see this in various things. You look at the little neighborhood, you have a little neighborhood, and you have a two-dimensional sphere. You also see this also in the Laplacian. The Laplacian has a green function that produces your potential, and so the electromagnetic potential and also the Newtonian potential and gravity, they are all 1 over r, which indicates that we are in a live in a three-dimensional space. But that's also happening here when you're looking at discrete structures where you don't really care so much anymore about this rigid manifold structure. I talked about this before. I still have to write this up. called this homotopy manifold, but homotopy manifold has been used kind of somehow. I will probably just rename it foam. It's a foam a structure, which is very, 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 very nice, because when you take any data of space and you look at or some manifold and you measure things, you never ever get the manifold structure before cleaning it out. But you don't care. If you just identify points which are close enough together, you connect them as a graph structure, you get these things, and you have all the algebraic properties, you have all the cohomological properties, you have all the connectivity properties, you have all the topological properties you want, you have the metric properties you want, you have the geodesic, you have the differential geometry, you have the right curvatures, you have sectional curvatures, you have Ricci curvatures, so you have everything you want. So there's no need to have a this rigid simplicity decomposition of space. You don't give a damn whether it's 10,000 dimensional when you are dealing with data. And actually, that's what happens when you deal with a point cloud and you represent the surface with you don't actually care whether it is whether it's a manifold. You usually want to reduce it to something which has a manifold structure, just that you, from the complexity point of view, so that you don't have to compute too much. So that was this a little bit. So the third one, here's the theorem. If I'm thinking I'm putting out too much hot air, then I'm proving theorems, and that's a theorem. So there is nothing to argue about the theorem. So G. Finite simple graphs. With curvatures. N of x, y in So what else? That's what happens in Euclidean space. Also, if you look at the mathematics of Riemannian manifolds, and you take the product of two Riemannian manifolds, and you have the right basis, so that the tangent space splits nicely according to the multiplication. Then the Riemann tensor, becomes block diagonal, and the curvatures are just of this Gauss-Bonnet Chern curvatures are just multiplied. So that has to happen. It's kind of like an axiom you want to have for a multiplication to be taken seriously when you also look at the differential geometry. So it is something which is kind of a little bit innocent. I stumbled upon this a couple of weeks ago. I tried to prove this combinatorially. You just actually go back to the definitions. I would be happy to see also a combinatorial, a direct proof. Did not succeed to do that, and there are indications that it's actually very hard, because what we will use is a product formula for Poincare-Hopf indices, and there we need the Euler characteristic. We need the Euler characteristic, and the Euler characteristic homotopy invariant, and we will have to see that these unit spheres, we will have to understand unit spheres in the product and see that it's actually homotopic to a join, which is dual to the discrete addition. But it's an addition. It's kind of a Sabidusi addition called Zykov join. And so what happens there on the Zykov join, these f functions are behaving nicely, and so then we can work. So this is still open here, but maybe I'll just show you some example here. I have in the paper also example. I have also code which allows you to do that. You can compute. You take arbitrary Erdős-Rényi graphs and you multiply them, and so also the code for the multiplication is there. And then you compute the curvatures, and you see that they are the same. So this is very useful, for example, to construct explicit manifolds where the curvature is constant. So if the curvature is constant everywhere, and your curvature is constant here, so you get also in the product the curvature is constant everywhere. It's kind of a neat thing. So this is the so we use integral geometry. Which is very natural if you look at Gauss-Bonnet. Chern was his advisor was Blaschke, and Blaschke was an integral geometer, and so there's a lot of Banchoff is kind of has made use of this integral geometry. He's a student of Chern, and so I mean it's no surprise that in this context integral geometry comes in. Came from as an outsider, I came to it completely differently, and just used it as a tool to prove that odd-dimensional manifolds have zero curvature, which is a Dehn-Somerville relation. By the way, Dehn-Somerville came back then just again as they are related to eigenvectors of the barycentric Riemann operator, and they are also related to symmetries which you have for this function. So the Dehn-Somerville spaces are much more general than spheres. So it's a very natural, very nice space. But this is what we are doing here, holds for any finite simple graph. It doesn't have to have a manifold structure, no Dehn-Somerville or any relation. This is true for any finite simple graph. And let me just tell you something about the proof. So first of all, I'll tell you about the index product formula. It's also something from 2012. Actually, I submitted this both together, and in both cases I didn't get even an answer. So, but what you have, or just that it's not considerable for a graph theory paper. But what we have is so this is a finite. This is in general. So this is a finite simple graph. And then we have GB to some ring. So I'm a little bit reluctant to use the real numbers because I'm somehow finitist. I don't believe in the real numbers, so don't need the real numbers. You can just take anything. You can, for example, take the integers here. So this is a coloring. Just meaning locally injective. You don't want to have the function should not have the same value at vertices which are connected. It's a very natural assumption which you want to have for functions. So it's kind of like this is the only non-degeneracy condition you really need. In the continuum, what I'm telling you here, this needs much more conditions, and then we define I G. We just call this because it also depends on G. So where S minus Gx is generated by all y in S x, leave the capital G away, such that G of y is smaller than Gx. So it's a stable sphere. This is a coloring here. I'll just maybe write it down here. And I call this here, this is Poincare-Hopf. And if you look at examples, kind of if you take a manifold structure and you take a nice function, this is really what you get. This is the Poincare-Hopf index. It's a degree of a sphere map, and you could quickly just look at examples and see that this is really the same thing. And so this is the Poincare-Hopf index, and it's very simple to see that the sum, so this is Poincare-Hopf. I'm proud that still until now I didn't find that anywhere before, so something people have missed. So this is a kind of the Euler characteristic of G is sum x I G. We just actually put also the capital G here. So it looks like Gauss-Bonnet, but it's actually, these are the divisors. So this is the divisors. So these are integer valued. So this is like charge, or this is this very spin, something discrete. So unlike curvature, curvature is also kind of in this case, these are rational functions in our rational numbers in our case, but these are integers. One calls a divisor. So there's also a nice theorem here, which is a Riemann-Roch theorem. Should talk once about that. It's very interesting, very rich story also in graph theory. But that's the result. So that's kind of the result we are needing, and so what we have is in order to prove this theorem here. So what we are doing, we first of all prove a theorem for these indices. These indices behave nicely. So what we have is a lemma. Let me just not repeat all the assumptions or anything. So what we have is I of G times H, and then G, let me just write it as tensor H x y is equal to I G G x times I G H H. Actually, why don't I just do G times H? Tensor sounds scary, but it's actually the tensor product. Also, this is actually tensor product here. So what you have is G times So these indices just multiply. That's very nice. So there are lots of properties which multiply. Also the spectra of connection Laplacians. Tensor, they are tensor, they produce tensor products here under this shadow multiplication. And the spectra just multiply, like in multi-particle systems. If you look at kind of this is a Fock story here built into the whole thing. And actually you can even complete it. You can actually work with completed things. You can look at waves of graphs, all kind of thing. You can look at the Dirac equation in that space of graphs. No problem. So that's the thing. So what we have to kind of see is, in order that this is actually not so, this is the key. And in order to see that, what we see, what is involved is this Euler characteristic of the stable sphere. So what actually happens is, what we have to show is, we have to understand the sphere of products. So if you look at the sphere of product, if you look at the S so there's a formula for that. So what we have is, so two, you see, if you look here, if you look at the thing, and you want to look at the unit sphere, in this case the unit sphere for that point consists of all this thing. So what you should see, what it is, it's actually a sphere times a ball, which is here, plus a sphere times a ball, which is here. And that's actually true in general. I mean, it's kind of just from the definition. So it's not the ball times the ball, because you have to take the point out. So the only thing which survives when you take the point out is, this is SGX. And then that's the product of BGY union S, that's H, HX BGY. What do I do? Let me just write it down. I want to use the X for the thing. So this is BGX multiplied with SHY. Just make the picture. So that would be the, if this is X here, this is Y. G. This is H. And what we have is, in this case, that's the so this is B. And the thing is, what we have is here. You see, in this case, it's an interval times a circle. Here, it's a 2-point set times a disk. So that's the thing. That makes the boundary of that kind of can. So that's the can. So the can, that's a sphere. It's made of 2 parts. So there are 2 parts on the top. So this is a 0-dimensional sphere times a 2-dimensional ball. This is a 1-dimensional sphere times a 1-dimensional ball. So, and that's actually homotopic. All right, here, this is the join. So in a manifold case, these are spheres. Also in a kind of more, less rigid definition of manifold, like I have talked about, these are still either contractible or manifolds, or spheres. And if they are spheres, then this becomes also a sphere. So what actually happens, but we don't need that. We are just in a general framework. We don't care whether we have manifolds or not. So this is finite simple graphs in general. But what we have in general when we take the join is the genus this is Zikov. And the reason is because more generally this f function, the f function is multiplicative. And so this is kind of just evaluating, this is actually just evaluating the f function at some point, minus 1. But this is called the genus because in the one-dimensional case, in a curve case, this is actually this is actually just the first Betti number, right? Which is the 0th Betti number plus the first Betti number is the Euler characteristic. So that's the number of holes, so to speak. And so that's what one calls traditionally the genus, but it's defined for any finite simple graph here. And so that's multiplicative. So because of this multiplicative, because of the homotopy and Euler characteristic, so because the Euler characteristic homotopy invariant, this actually, because this is the join, by the way, the join you can actually also visualize. The join is this, right? So this is S0 plus S1. S0 plus S1, that's the 0-dimensional sphere times the 1 plus the 1-dimensional sphere. That gives us the 2-dimensional sphere, this double cone. And so that's what's called a suspension, which is just adding S0. And so what is the result? These are actually homotopic. These are homotopic. And so this is very nice. And because they are homotopic, they have the same Euler characteristics. So this multiplies, because this multiplies, also these indices multiply. But you see kind of why the struggle might come from a direct combinatorial proof here. So what you have to show is, because there's some homotopy coming in, so there's some magic will come in when you're doing this combinatorially. I'm pretty sure it's possible, but probably hard. You have to kind of do some magic. You have to kind of see some cancellations, things like that. So, but that's this lemma here. And just for the proof is now just almost finished. So the proof. So first of all, if you have a probability space of such functions here, of colorings, so omega and we write E expectation. Then if you look at Poincare-Hopf, at the Poincare-Hopf formula, and you look at the expectation, taking expectation of Poincare-Hopf gives Gauss-Bonnet. I like this very much because this allows you to do much more general curvatures than this. This curvature you get this when you take, for example, IID random variables on every vertex. So with probability 1 there's a coloring, and so if you take the expectation, this is what I showed also in 2012. So 2012. So you also have this. You get Gauss-Bonnet directly from that. But you can take any probability space. You can take the probability space consisting of one point. It's actually kind of all the probabilities concentrated on one point, and then you get just Gauss-Bonnet, Poincare-Hopf. Then you just get Poincare-Hopf. So, but what happens is if you take, for example, the space of all colorings. As I see the chromatic number, to take all the colorings with this chromatic number, then you also get this curvature here. Just this is the most symmetric curvature you can get. And then we have to notice that I, G, G, X, and I, independent. I mean, if you take the product probability space here, you take the product probabilities. You take the product probability space here, and what you are getting is now you can just take the product here. So what you have is a kx. Is the expectation of IGX ky. It's the expectation of IHY. And when you look at the product, what you get is the k g h x y is the expectation of IGX times IHY, and by independence, what you can do is you can split it up. So that finishes the proof of this product formula. And it's nice to see kind of a little bit of additional structure coming in. You see that it's not totally obvious. And also nice to see that this Shannon ring is really a very, very natural notion in graph theory. It has lots of compatibility, algebraic topology, but also, and that's what we have just seen here, in a discrete differential geometry. So, and that's it for today.